Okay, kind of excited to hear that little bit of tidbit there later on, maybe. Okay, so I'm gonna start on our next section. Should have about 50 minutes before the end, and then I think at the end of the day, I do a class. Towards the end, I'll start getting to the exercises. I will record them, so you don't need to hang around. But if you have any problems with the exercises, hang around at the end, and me and Alan hopefully should be able to address them. So just one last recap. I'm going to say this continuously. I am deliberately not showing you all the arguments and all the things behind everything. They are in the exercise of what you need. For example, but I always recommend, anytime you get lost, anytime you have a new function, have a look at the examples, have a look at their works. There's so much information there, and even before Googling, that's the place to go. So the last bits here are now conditions and loops, which are, I think, essential for our class. And then functions, which aren't essential, but you should know. So we've already looked at using logical vectors as a way to index other data types. So x is 1 to 10, and then we can use the logical, which is created to bring x is less than 4 to pull out from our vector just the elements where that's true. Okay. We can also use logical to control the flow of our code using here conditionals. So these two things we're going to do are conditional branching, which are typically, I'm sure there are other things which do it, which is if or else, clauses, and loops. So probably the most common loop we'll use is a for loop, but there are while loops as well. So while I'm analyzing data, if I need to execute complex statistical procedures, if that's true, I'm going to use R, else if that's false, I will use a calculator. So conditional branching is the evaluation of a logical to determine whether a portion, a chunk, code is X. So in R, we can use this if statement with the logical to be evaluated in round parentheses and the dependent code to be executed. And I think this is the first time we're going to see it in these kind of curly brackets. Is there a better word for these than curly brackets? So let's have a little look at this in a very simple example. I'm going to explicitly set X to be true, right? So that makes X a logical vector of length 1 containing one value which is true, right? Our Boolean. So we're going to have our if clause here, if, and then like I say, we're going to put the thing which will be evaluated into a logical here inside these brackets, these round brackets, parentheses. And then all the code we want to execute, we're going to put in this expression, we call it, but in these curly brackets. This will be the code which is evaluated if X turns out to be true. So in this case, I've set X to be true. When it gets evaluated, X is going to be true. Right? So we're going to evaluate this bit of code and it's going to print. Here I've got this function called message, and it just does exactly what it says on the tin. It messages to the screen. X is true. If I change now X to be false, it's going to go if, it's going to try and evaluate X. X isn't true, it's false. So we don't get this message, right? It doesn't go inside these curly brackets. It doesn't evaluate this expression. So I don't get the message, okay? Just a side note here, if you are giving yourself messages in your code, if you want to print stuff, don't use print, use message. The reason being is message we can silence, print we can't. So when we start to get into making nice reports, we may want to turn off all our messages because maybe they're just for us. This is now happening. You know, it's a simple way of debugging. We can just set a global parameter and we can silence all our messages. We can't do that with print. So always use message. I think that's pretty much all. Unless you don't ever want it to be silenced, don't use print. Okay. Most often, we're not going to just know and pass in X is true. We actually want to evaluate something. Okay, that's the whole point of these if statements. So let's do our first actual evaluation. So here we're going to set x to be 10, y to be 4. And then we'll evaluate, is x greater than y within our brackets. So in this case, 10 is greater than 4. So it's going to go inside our expression, and it's then going to give us our message, which is this. And then I've got a comma here, and I can actually put in x, comma, the rest of the message, comma, y, and I'll get a message. The value of x is 10, which is greater than 4. Great. If I then change y now to 20, this if statement is no longer true, right? 10 is no longer greater than 20. 10 is never greater than 20. So I don't get that message, right? I can see here the message is printed. Here it's not. So that's kind of worked. But we probably want to see still some message, something about what happened. Okay, just no message is maybe not the best way of doing this. So we can actually add something called else. Okay, so in this case, this is a little harder to see. I'm going to do the same setup where I'll have an if, and then I'll have my expression. But then at the end of my first expression, immediately following it, I'll have else, and I'll open up another expression and more curly brackets. And then there, I'm going to put a message, x is greater than 5. So the first one is it's less than, second one is greater than. So now what's going to happen when I set x to be 3, it's going to come in the first time here. This is going to be true. So it's going to evaluate this. And then there is no else, right? This evaluates to be true. And so it's done that, and then it will skip past the else and continue. If I change now x to be 10, x is no longer less than 5. X is 10, right? So it won't go into this. It won't evaluate this part of the if. It will skip down to else, and then we're going to get x is greater than. Okay. So in this case, we have one conditional where we're really checking something, and in every other case, it's going to go to the else, and that's not good.
So you need the else to be like indented.
Yeah, in this case. Sadly. So R is pretty good for indentation, etc. But in this case, yes, it do. So here we're going to try something a little bit more snappy, I guess. We're going to try and evaluate multiple conditions. So what happens if maybe we want something different to happen? If the first one's not true, we then want to check another conditional. If that's not true, okay, then we will evaluate to the kind of default else. So we can actually use else with another if, kind of set up like this, where we'll have if, and then after the first one, we'll do else if, and it will evaluate this one. And then if that's not true, it will skip down to the else. Okay. So we can have any number of else ifs. We can have more and more conditions and catches, and there are other ways, including a function called switch, which will allow you to catch multiples. But this is a nice, easy way. If x is greater than 5, I'll print that first message. If that's not true, then check, is x equal to 5? Okay, none of that's true. It's going to go down to the else. So your else is capturing basically everything else apart from the ifs. A really kind of nice, useful function, or I find a useful function, is if else. So if else is kind of a way of doing or evaluating conditionals, giving us a result. So here we have a vector 1 to 10. And if else, it takes the logical we want to evaluate, and you can provide then, if it turns out to be true, it's going to return this first result. If it evaluates to be false, it will return the second result. Okay, so we have a vector here 1 to 10. I'm going to give it the conditional if else x is less than or equal to 3, less or equal or more. And then we can see it returns then a vector less or equal, less or equal, less or equal. And then by that point, we're now no longer satisfying that logical more. Does that make sense? Yeah. Okay. So it's basically taking this vector, and for every position in the vector, it's evaluating whether or not it's less than this, or it satisfies this. For the first three positions, it does, because it's less than 3, equal to 3, but we're less than equal. And then every other position, it's more. Ooh. I think when I compile it, it makes it a clever one. No, sorry. Yeah, I see what you mean. Yeah. So I think this is just the nature of me compiling this, and it looks better. Sorry. If we want to get more, oh yes. Sorry. You can only work with that. That's a good question. I like that. Maybe you can do it in a matrix. Let's check that. I'll check that. But really, it's very useful for turning a vector like this numeric into something like this. And I use it a lot to actually create factors. Because I can evaluate my numeric and then I can build categories from it. And you can actually make it kind of complex depending on whether or not you find it readable. So in this case, I'm going to do a nested if else, right? So it's going to have here x equals 3. So first it's going to evaluate my vector, and it's going to check every value and say, is it less than 3? Or sorry, is it equal to 3? It will put same. And then for every value where that is false, it's going to evaluate it again in another if else. And now it's going to check whether it's less than 3. And it's going to put less or more. Okay. So now I've got slightly more complex way of evaluating my vector. And I'm going to get the same first, and then it's going to evaluate the ones which are false. So the first ones were false, but they then satisfied the second if else. So they're less, otherwise they're more. Okay. So it's just a really nice way of, I usually use it for turning vectors into strings or categories typically, so factors. But now I'm going to check if I can do it with a matrix as well. Okay, so given we have conditionals, so we can do if or else or if else, we then may want to actually start to be able to loop through our data. So maybe we have read in multiple data frames using that import function in Rio. We now have multiple data frames in our list, and we want to loop through every element in our list. So we really have two main ones for doing this. We have while, and we have for. So while loops repeat the execution of code while a condition evaluates as true. So I usually use this for reading a file. While I can still read this file, while I still have a line, keep reading. Eventually you don't have a line, just stop. For loops repeat the execution of code for a range of specified values. So 1 to 10, loop through them. For every element in my list, loop through them. So for loops kind of loop through a specific range, while loops keep going until a conditional is false. So let's start with while loops. So here I'm going to set, this is a really good fun exercise. Everyone makes the same mistake. So let's set x to be 1. And then we're going to set our while loop, and our conditional here will be x is less than 3. So while x is less than 3, it's going to keep on performing this loop. So I'm going to put message x is x, whatever the value is of x is. And then I'm going to increment x. Add one store of x by doing x is now x plus 1. Okay. So then first time it goes through the loop, x is 1. Right, so it's going to come through. X was 1 up here. X was less than 3. It gets the message first. Then it increments x. It's got to the end and it will reevaluate this. X is now 2, still less than 3. So it's going to print this message. Then it's going to add x is 1. It's going to add x plus 1. So now x is 3. It's going to come back to the beginning of the loop. And that's no longer true. So we'll finish the loop and it moves on to this line. So I say x is not less. A common mistake people make with while loops is not incrementing your x, right? If I missed out this line, X is always going to be less than 3, and you end up with this infinite loop. And I think in the exercises, we're going to get one where you may forget to increment, and you're going to end up in a permanent loop, and your R won't stop. Control C, stop your R. Okay. But it's deliberately there to catch you, so you don't end up looping forever somewhere else. 4, which I think I use a lot more often, really allows the user to cycle through a range of values, applying an operation for every value. So here we're just going to cycle through a numeric vector and print out its value. So for I in X, so X is a vector of 1 to 5, 1, 2, 3, 4, 5. So I've done the shorthand colon. So the first time it goes through, I will take on the first value in X. It's going to loop through it. So for I in X. So the first time it goes through the loop, I will take on the first value of X. It's going to print it, will be 1. And then go through to the next value in X, which will be 2. It's going to print it, print it, print it, print it, until it gets to the last value in X, which will be 5. And then it will print that, and then it's done. Here I've slightly updated message. I put append LF equals false. I guess it's append line finalizer. So it's not putting an end of line. So it's going to print them all 1, 2, 3, 4, 5, 1 line. Sometimes that's useful. You may want to do that. We can loop through anything which has an order and a length, or even doesn't need much of a length. It can just be 1. But anything with an order, we can loop through. So we can loop through vectors or lists or factors even. So here I'm now going to create, when you install or just open R, you automatically get some objects available to you. One of them is letters. So if you just type in letters lowercase, you get all the letters of the alphabet. If you actually type in letters uppercase, you get them all in uppercase. So here I'm just going to take the first 5 letters in the alphabet, deliberately applying a function which is toUpper. It's going to turn your things into uppercase. And then I'll loop through that. And as you can see, I can loop through that just in the same way as I did previously. But rather than looping the numbers, I'm now looping through letters. And I'm messaging them. First time I go through, first letter's A, I come back. Second time through, I now takes on the second value in X, which will be B, C, D, and then E. Okay. We've got lots of exercises on this. Sometimes we actually, sorry, yes. Yeah, I'll come back and I'll show you that at the end. Just a bit of time. So one thing you might want to do is really loop through 2 things, right, at the same time. And there are lots of ways to do this. But if we know that they're in the same order, we really just need to loop through like the positions. So if we have 2 vectors and we know they're both length 3 and they're in the same order, so they correspond to each other, we just need to loop through the positions. Okay, so to loop through the positions, all the index positions, we can actually just do 1 to length gene name. Length gene name will be the end. 1 will be the first position. So in this case, it's a length 3. If I do 1 to length gene name, I will get 1, 2, 3. Okay, so that's every potential index in my gene name, which I know will correspond to every potential index in the expression. So this is probably the most common way you'll do a loop. For I in 1 to length gene name. And now I can't explicitly just message out I, it's just the index. But I can do message, gene name, and then I can provide square brackets I, and it will pull out the first time it goes through, it will pull out the first index of gene name and the first index of expression. And as I loop through the second time, I get the second index position, third index position. And now I don't have append LF equals false. So I will get this, and then I should get this, and then I'll get this. Okay. So the difference here is I'm not explicitly looping through gene name. I'm just looping through the positions of gene, I in 1 to 11. How much more have we got in this? Okay, great. So then we can combine them all together and make some really complex things. Right? So we can do here a loop where we're going 4i in 1 to 3. I'm not sure why I set it. But I'm going to loop through the values of I in this 1 to 13. And as I go through, I've got 3 conditionals I'm going to evaluate. First time it goes through the loop, I will be 1. So I isn't greater than 10, I isn't 10. But in the end, it is this last one, because it's none of these ones. So it's got to be this one, else. And it's going to go number I is less than 10. So if I look here, first time it goes through, they're all false. So it's going to go to the else, and it's going to continue up until 9, where finally this second one is true, and it's going to print what's within this expression. And then once it's above 10, actually this is going to be true, and it's going to start printing just off the screen here that I is greater than 10. Okay. So just to show we can actually do loops, and we can nest within them conditionals, and we can start to do some kind of complex evaluation of our vectors or what other objects we're looking at. If, and this is probably more useful for while loops, but if for some reason we decide that we want to stop our looping at a particular evaluation, we can use this function break. Actually, it has no arguments, right? So we just type in break here. And in this case, once we get to this line, which will happen when I was 10, it's going to exit the whole loop. Right? So it's no longer going to continue to evaluate. It just stops. Okay. So here we get to 10. It should continue through 11, 12, and 13, but because it met this break, it's just over. There are, and I'm going to stress that there is no speed advantage of using these. In fact, it's a little bit slower than doing a loop, but not much slower. But there are some nice shorthand functions which allow you to kind of operate over matrices or lists or both in kind of a single line. And they basically allow you to apply a function to every element of a list, or every row of a matrix, or every column of a matrix, or every cell of a matrix. Okay, and R really tries to make for neat code. And I would say the real advantage of this is neater. Apart from that, another advantage of using some of these functions, which allow you to loop over things, is that there are parallel versions of them. Okay, so my favorite function, one of my favorite functions is BPLApply, which is BIOC's parallel version of lapply. So we're going to run lapply, and it will work in succession, serial, across our computer. If you use BPLApply, which we'll show you later on, it will send every job off to a different node on your computer, different CPU. So you can imagine it'll be a lot faster. Okay. So learning how to use this can be very useful for that. sapply is also kind of neat, and we'll see it actually applies. But no, I want to stress no speed advantage here. Just want to check, am I still recording my face, or are we recording something else? So there are functions that allow you to loop over a data type, apply a function to the subsection of that data. So apply will apply a function to the rows or columns of a matrix or data frame, and it returns the results as a vector, matrix, or a list. lapply goes through every element of a vector or a list and returns the results as a list. sapply, smart apply, applies the function to every element of a vector or list and returns the results as a vector, matrix, or list. But it's going to try and return a matrix to you if it can. If it can't, it will return a vector. If it can't, it will return a list. And in some cases, this is very neat. So let's look at apply first. And apply is very useful because it allows you to operate on matrices. So it applies the functions to the rows or columns of a matrix, or both. We can apply it to cells. And the argument fun specifies the function that you want to apply to that particular row or point. So we have apply, we give it our data, typically a matrix, can be a data frame. We give it the margin. So I say 1 if I want to go across rows. So if I'm going to get the mean of rows, I'll put 1 there. 2 if I want columns. And then 1 or 2 for cells. I don't think I've ever used that. Nope. So let's have a go and let's build our matrix. So here we have a matrix, 1, 2, 3, 4. So it's 1 to 4 and it's by row. So we've got 1, 2, 3, 4. Now, if I do apply, I give it that matrix. I tell it 1, which is for rows. And I just, like I said earlier on, it's very common. 1 for rows. It's also rows come first, columns come second. So here I'm going to get the mean of every row. So I'll do apply matrix rows. I get the mean. So it's 1.5, 3.5. If I want to get columns, I'll do this, but I'll now set that to be 2. And I'll get the columns back as a vector. Very simple. Useful, we're talking about paste earlier on, and there's additional arguments of things like collapse. Useful if I want to apply, if I want to provide additional arguments to this function, right? It's a little tricky, but some of these functions we know take multiple arguments. I can actually provide them after the comma, after the function. So we had someone here asking about like pasting things together and we ended up collapsing. So in this case, I want to use collapse. So I'm going to hit my matrix. I'm going to go by rows. I'm going to paste. And I'm going to say collapse equals colon. And now I get that string where it's kind of pasted these 2 elements from my row. But now it's collapsed them and it's put like a little colon between. Okay. So additional arguments to your functions you can specify after the argument, put a comma. I can put an argument there. I can do another comma, provide another argument, paste, however many arguments I need to supply. Similar to apply, lapply applies a function to every element of a vector or list, but it's going to return a list to you. So here I'm going to do lapply of this vector and take the mean of basically 1 and 2 separately, which is star. But I'm going to get 1, 2 mean, and then I get 1, 2. The mean of 1 is 1, the mean of 2 is 2. Right. But notice it's come back as a list. Similarly, I'm going to work on a list here. So I'm going to loop through this list. The first element is going to be 1. The second element is going to be a vector containing an NA and 1. The second element and the third element will be 2. So if I did this without any additional arguments, I would get 1 warning 2 or 1 NA2. But I'm going to supply to mean an additional argument here, which is very useful. NA.rm equals true. I'm deliberately showing you this argument because a lot of time when you take a mean of a vector and there's an NA in there, you just want to ignore it. So we think about why NA, but often we just want to ignore it. NA equals RM, we remove them before it takes them. So that's a really useful argument for mean there. And in this case, we end up getting 1, 1, 2, but again, a list. Okay. Which is in some way you can imagine you may then want to unlist it, like we showed you earlier on, and if you get enough results, maybe put that back into a matrix. sapply, smart apply acts like lapply, but a return attempts to return the results as the most appropriate data type. I think it kind of has an order that it will try and return a matrix. And if that doesn't look sensible, it will try and return a vector. It can't do that. So here I'm going to get a vector. I'm going to do sapply on my vector. I'm going to get the mean. I'm going to do NA equals R true to get mean 2. And it gives me a vector back. I can also give it a list, and it still gives me a vector. So vector, it feels better than giving you back a list. This starts to get much more useful when you're starting to operate on things which are a little bit more regular and can be forced back into a matrix. So here I'm going to create a list. I'm going to have row 1, 1 to 5, row 2, 6 to 10, row 3, 11 to 15. See, we have a list, name for this, row 1, 1 to 5, row 2, 6 to 10, row 3, 11. If I was to do lapply on this and ask for the quantiles, quantile was a function, it would give me back the five quantiles of the data. Okay. So I have a list and I have the results for every list element I evaluated. That's not so bad. But that might be kind of tricky to work with. If I apply sapply to that, it does something kind of neat. We're actually going to give me back a matrix, same function, same input. Right? But by doing sapply, it gives me back a matrix. And not only is it giving me back a matrix, it's actually giving me some sensible row name, column name, and then it gives me the quantiles they correspond to that. So sapply can sometimes be really nice and useful. It's not always predictable, but sometimes in your work, it can save you the effort of having to convert your data from a list into a matrix. But it can't always do that. And I think I've deliberately given us an example here, where if I take the summary of a data frame or the summary of a vector, they give me kind of different objects back. In that case, when I try and do sapply on this list I create here, see I get a list back. It couldn't turn it into a matrix, it couldn't turn it into a vector. All it can do is create a list. And then it names them for the result back here. I get a list back. I'll have to work out how to deal with that myself, what I actually wanted to do with it. Okay. So we have an exercise here. We're going to come to those at the end. So I just want to talk about functions. So I think functions is the last thing we cover today. At the time. And please feel free to ask questions as we go. I'll come back to your question at the end, I promise. Absolutely. So you don't need to create any functions in this course, but I recommend you do it because it actually makes tidying up your code quite nice. And often people in your lab, your colleagues, your friends, they want to have your functions. It's a nice way of sharing. So we can create a function really from expressions kind of easily using this function. So the setup of it is very much like this, right? So everything after the curly brackets is what we call an expression. Okay? So that's what's to be evaluated, and you'll have the code to evaluate in there. We have a return line using this return function. So this is what the end result of calling this function, this is what will be passed back to you. Okay, so like when we do mean, it passes back a value, which is the mean. This is what's going to be passed back. And here we have the function, right? So this is us building the function, and we're going to create a function called myFirstFunction. Sweet. And we're going to give it the arguments which we want to pass it. In this case, this is our argument here within our function. So this is the expression we're going to get evaluated. This is the argument we want to be able to pass to our function. This is the name of our function. When we were to run this, and we don't know what it's going to do, we would do myFirstFunction, just like we do with other functions, brackets. Then we would have one argument we need to fill, my argument, corresponding to here. We give it a value. So let's create a really simple function. So myFirstFunction, I'm going to create it by assigning it to myFirstFunction. Function. Within those parentheses, I have two arguments, num1, num2, separated by comma. Okay, and then we have inside our expression, so where these quotes are, we're going to create something new called sumNum, which is just num1 plus num2. And then we're going to return that here back to the user, back to ourselves. Okay. So in this case, I'm then going to run this. Once I've created this function, I'm going to run it, and I'm going to give it, for the arguments num1, I'll give it 2. The argument num2, I'll give it 3. And now if we look, when I run this, it should pass back this sum num to me, and it should be 2 plus 3. And that's exactly what it does, right? Give me the result 5. Yes. No, not at all. Not at all. So, once it gets long, you might want to specify all the arguments. We might have defaults, but right now, exactly that. I don't need to put, I could just put, you were saying I could just put 2 and 3 there, not that. Yeah. I'm just being explicit. Yeah. No, you're 100% right. I just need to put 2 and 3 there. I'm putting it here sometimes just for readability. We'll come back to that as well. So here we can make this a little bit more complex, and maybe we want to do a few things and then return this back to us, right? So maybe I don't want just the sum, I also want the multiple. If I'm going to write a function, I might as well do multiple. So I'm just going to add multiple num, and then I'm going to return some num and the multiple num with a comma. So when I run this, it's going to give me an error, and it's going to tell me exactly why multiple argument returns are not permitted. Some languages they are, right? You can return multiple things from an argument as long as you assign it to multiple things. Here it's not. So I can't just return multiple things back because I'm actually only assigning it to one object. So what would actually happen here? Right? It would be some combination of some num and multiple num, but I have to explicitly do that in the function if I'm going to return. So the solution to this is to create an object which contains all the results I want. Then I pass it back. So all I have to do here is create a vector of results. So I'm going to concatenate some num and multiple num together. I'm going to give them some names so that the user would understand the output. And now I've got the return the vector of results. So when I run this, I don't get an error. I get a nice vector saying the multiple is 5 and the sum is 6. Yeah. Multiple was 5 and the sum was 6. Often, this is where lists become really useful. So maybe you're returning multiple different types of objects. Returning a list, you know it will contain any potential objects you have. So in this case, I'm creating a data frame, and I'm going to return not just the result as my result data frame here. I create the data frame for my results. 2 columns, 1 with sum, 1 with multiple. Have a list result is that. I'm also going to provide the input numbers. So input numbers first number is none, second number is 2. And I'll put that as another element to my list, and then I will return the whole list. And that's often how I build functions. I have a list or something if I'm doing complex things, if I want to return multiple things. Okay. Something to remember here is, so every function I have, I'm putting return here, right? And it happens to be the last line. But it doesn't need to be. And if you have return in your function, it will stop as soon as it hits that return line. So I'm going to put a message here after return. I'm going to have a message before. This is what we call a terrible way of debugging. Simple way of debugging. As I run this now with my 2 values, see I get that first message, the second message I don't get, but I still get the result. And that's because as soon as it got to this return, it ended the function. But you don't actually need, I think it's good practice to put it in, but you don't actually need a return line. In some cases, when you're just coding very quickly, you actually can just rely on the fact that when you have a function, the last line will be returned. If I have no return statement, it gets all the way to the end and it will pass that last line back. So actually, I don't need to assign it to this. I could just list that way. This way, I will get exactly the same result, whether or not I put return there. I think it's good practice to put return there. It makes it a lot easier to read. People can kind of skip and look for the return, but you don't need it explicitly. Just the last line will be sent back unless we do explicitly put a return, and then the function stops there. Okay, now we'll get something a little bit more complex. This concept of scope. I think Matt wrote this last bit, so I just want to, there we go, sweet. Come full circle. So, does anyone out here know what the concept of scope? Alan, you're not included in. Does anyone know what scope is? Java? Okay, no, that's fine. No, absolutely. It's probably called something different in Java. So, scope is really like variables defined in an argument or within the function exist only within the environment of the function. So only when this function is running do I have access to this. So here, within this function running, I'm creating something called sum. When I'm returning it. Right? But so I can run the function, and the result from sum is assigned to here. But sum, if I type that in, isn't available. It was only available when this function was running to the internal environment. I'm not creating it, putting it into the external environment, which is great. Life gets a lot more confusing when we start doing them. That's it. Yes, sorry. Yes. So that shows you how long ago I did it. So here we're going to do something a little bit the other way around. Vectors defined in the global environment outside the function are available within the function. Okay, so this can cause problems, and when you forget that you've defined something outside the function, maybe you forgot to define it in the function at all. You're using something which is defined as. So here I've got num1, num2. I'm going to add num1, num2 to this third number. I'm going to return sum num. Right. Then when I get my result, I'm going to get 2 plus 3 plus 4. That's actually bad. That's bad practice, right? We don't want our global environment to affect how our function results work. And often this will get you won't even notice this until you clear out your environment and you try and run your function. And it will say, this isn't available to me. If I had just run this and then I ran the function, with no error, it keeps finding this. So that's something to keep your eye and watch out for a bit. Okay, changes that we make to a variable. In this case, my third number here, I'm actually going to change within my function. My third number, I'm going to use it here. I'm going to assign the addition of num1, num2, my third number to this variable, my third number. I'm going to return it. And what I get back is 4 plus 2 plus 3. So I get 9. Which will assume that my third number at some point within the function got updated. But once I'm back out of that function, my third number retains its value. So I can't change variables that I have outside my function from within my function. This is like its own little private. It can see what's in the global environment, but it can't edit it. And that's kind of the concept of scope. And then we get something I recommend you never do. So we talked about this special operator. It's an assignment operator. Slightly different. One thing is that we can add another arrow there. And then this assignment actually becomes a global assignment. And in this case, by doing this explicitly, I can update my third number. So it's 4 here. I'm going to do 2 plus 3. You get my result, it's going to return this 9. But because I did this double assignment, I actually ended up updating it. There are very few instances that you ever need to do this, apart from maybe we're starting to do graphical user interfaces in Shiny. There are some cases you might need to do that, but basically never. But it's a nice example of why we have a slightly different assigner in R as well, rather than just using equals. We have this assignment operator and we can do this. So as we were talking earlier on, functions potentially can have defaults. Okay, so in this case, I want to give defaults to num1 and num2. Maybe there are something sensible. I'm going to assign 1, 3. Now, when I run my function with no arguments, it just picks up the defaults. Right? So it's going to go, I haven't assigned num1, I haven't assigned num2. So it's going to take num1 to be 1, it'll take num2 to be 3. I've still got my third number in here for some reason, but it will then run that function and do so. I can also then run my function and update these arguments if I want to, and I can do it more the way you were suggesting earlier on, where I don't explicitly name the argument. But here I'm going to say my first one's 3, my second one's 4, and I will override whatever it is. Most of the time, arguments may have defaults. Okay? If they have defaults, you don't need to actually explicitly write them. Sometimes you'll have, like say the dir function, the first function we looked at, it's got a default for every argument. Something like mean will have no defaults. It just doesn't make sense to have a default for something like dir. It makes sense to, if you're going to look in a directory, you might as well look in the one you're already in. So then we have a custom function example, which I think we lose later on. So this is a nice example, which is effectively take a z-score, which I believe is provided by the standard notation. Do a log space on that. So here we have a function where we can have my number, have my vector. Oh yeah, so it's going to tell you the z-score for a value given a vector of values. Okay, so first we take the mean of the vector. It's going to print out a message there. We're then going to have my number. So how far away is my number from the mean of the overall vector? Then I'm going to get standard deviations for my vector. And then I'm going to find how many standard deviations is my value away from the mean of all values in that vector. Okay, this is something we do for heat maps, for RNA-seq. It's one of the normalizations for single cell. I'm not sure if it's that popular anymore, but it's one of the normalizations. And then we return this. So here I'm just going to do this for our norm, gives us a random distribution of numbers, right, around 20. And here I'm just going to pass it in one value from here, give it my vector, and it's going to tell me, it's going to print this message because it prints it here, and then it's going to give me back a z-score. If, I think we'll do this in practice, if you're not really sure what's going wrong with your functions, maybe once I've finished class, I can show this. There are two really nice ways of kind of debugging how your functions or how they're operating. And that is debug and undebug. So debug will start debug mode for a particular function. Undebug will turn. So I think I probably have to show that in action if I can. So let me define a function. My fun. Three. That's a very simple function. I'll return the last line. I'll do it properly, so I'll do return code. And then it takes one argument, say x. I'll try and run this. Okay, so now I have my fun. Takes one argument. If I just press that, it's going to return it. So if I give that the argument now, it's say 2. It's going to give me an error. It's going to say L not found. Something I haven't defined. But if I really want to go through the function and see this in action, I can do debug. Then the name of my function. So here my fun. And now when I run this, you can see it's actually going to start kind of working through my function one line at a time. So I'm going to try and move stuff around a bit. Here we go. So right now, if I press X, X is 2 because I'm inside my function. I don't think I've defined Y yet. Nope. Press enter. Let's run that line now. Let's run the Y equals thing. Oh no, maybe now let's run Y equals thing. Okay. So now I've actually evaluated this. I'm now on this line. And now I probably have evaluated that, so I can see the result of Z. Everything's looking good so far. But then, you get to the line which actually breaks. So it's just a way of stepping through your function one line at a time and waiting or seeing when it breaks. And often it's still working at this point. It's still working. Okay, this line's wrong. And then I will start to kind of work on that line. Typically, I will do. I know it's which line it broke on. So I know I can get to this point. I know I can get to this point. That line killed it. So maybe I would run those first 2 lines. Jeez, this is slow, sorry. Yeah, sorry. My computer's jumping ahead a bit. Okay, so now I can see that line. I know it's going to break there. And I would kind of look at it and I'd say, well, Z looks fine. What's L look like? And I'd realize, oh, wait, I don't define L before that. So the issue is now is that, I'm done debugging that. Every time I run that line, it's going to debug it for me. So I just need to do undebug and give it my function. And now it will just break without any of that stuff. Sorry? So it really is. So the problem I find with often when I'm running a function is that I don't get to see the values within the function because they only appear once the function's running. So by debugging, I can run that first line and I can see, okay, now Y's been assigned that. And then I can run the next line and say, okay, that line works. These are what all the variable values are. And I can usually get to a line which I know is going to break, or it shows me this line breaks. And I can kind of look and say, well, if X was now a character, I now understand why that line breaks. So you can kind of work through one line at a time within the function. No. Okay. We're going to get some nice examples of debugging functions as we start to look for those one. Am I sharing screen? Yes. Okay. So the nice thing about some of these custom functions is that, once you've written your custom function, you can then use it with apply, you can use it specify, you can use it apply. You just supply it like you would a normal function. You supply your arguments here, just like we did before. So that's a nice advantage of writing your functions. And then use them in things like sapply, lapply easily. So I think we just got a few things here. I want to show you. So we already saw libraries, right? I already showed you this. You need to be the libraries can be loaded in R once you've installed them, just by running this library function. So you go library, and then you can do the name of your object. It doesn't need to be in quotes. The name of the library you want to use, and it will load that. If you want to see what libraries are available to you, you can just run library with nothing in there, and it will give you a list of all the libraries you have. More usefully, if you're using POSIT in RStudio, okay, you should have this window packages here. Man, my computer's slow. But if you open that up, it will show you all the packages you have. And if you want to load them, you can actually just click here, and it's going to load that package for you. I don't know what Destiny does. Sounds like a cool. Oh, it creates diffusion maps. Great. Good. If I want to unload it, I click it again, and it will detach it. If you click this, then it will also give you the help for it. So you can go through all the help pages we just looked at. And you can also actually, from this page, uninstall and update here. Another place which I didn't show earlier on because I was worried about my computer blowing up. Tools, you can install packages here as well. And by default, I think I show you later on how to add it, but by default, CRAN's already here. So if I start searching here, it's kind of got an autocomplete. So if I wanted to get ggplot2, that's another way that I could do it. Always leave install dependencies on. I just click install, and we'll go install it. Okay, so we don't need to necessarily do it in the command line. We can use this, and actually this is kind of helpful. We're not going to do it, but if your friend passes you their personalized package or whatever, you can also install them from tar files. But we're not going to do that today. Cancel. Okay, fine, skip up. Oh yeah, there it is. Tools and install packages. That's a really useful package, HMIS. It's just this miscellaneous set of tools from one guy which he reckons was missing from R. And actually contains everything you ever wanted, which is missing from R. Fantastic package. Install packages HMIS. You can look at that. So the last thing I'm not gonna go too much detail here, because I don't think many people do this. Do you ever do this, Alan? Only once. Exactly. So doing stuff on your laptop might not always be feasible. If you know Jason, I mean, if you're in Rockefeller, maybe you're not, but wherever you are, Jason has interactive R studios you can use. So reach out to HPC, IT_HPC. But often you just need to package you want to package your R script such that maybe it runs a particular analysis and then it writes out a result. And then you pick up that result later on and do your downstream analysis. Maybe it does lots of processing, but you're just interested in the, say, Excel file it writes out or something. Okay. So scripts, we've been actually doing in R for a while. So we have here, this was our scripting panel here. If I want to save this, there are a few different ways. We're going to show you R Markdown in a few sessions, maybe next session. So that's a better way of doing it. But you can do file, save as, it will save it. You can also load scripts here. Another thing to think about is actually, I've been working on this. I've got all these objects I've created. How do I save my session as a whole? I can do session, I can do save workspace. So that's going to save everything in my environment. And if I do that, it's going to save it as an R data object. And then I can load that .r data object later, and all those objects will be loaded back into R for me. I can also do save. I can list all the objects I want to save. Maybe here I can maybe I can save my fun. And I can do file equals my fun. No, maybe not. It's going to be a list. Sorry. Oh, no. Valid first argument. Jeez. Maybe I got that wrong. Oh, sorry. Jeez. Is that right? So here I'm just using ls, which actually is all the objects. ls is all the objects in my current work. Some other stuff I'm actually working on while I'm actually doing analysis on them. Okay. But often just doing session, save workspace. That's one. You may notice actually if you just click RStudio, it opens up your previous session. Do I not do save RDS? Maybe I'll do that. So R allows us to save and reuse functions, etc. So let's say we have an R script. I've saved my script and it's full of all the functions and I want to use that later on. So maybe over time I compile a set of functions which are just useful to me. maybe sets of variables I want to load. Some people have color schemes, which they want to put in a particular R script. That variable contains all the matched color schemes they want. If you do that, you can source R scripts. If by doing source, the path to the R script, and it will basically evaluate everything in there, and then it's available to you in your current R session. Okay. If you want to run R scripts from the command line, we can actually do that two different ways. We can do that either using R script. So if I'm in the command line, just running R will open up R for me. R script is like a non-interactive version of R, and it effectively runs the entire script and just saves the result. Okay. We can, and we want to set this -- vanilla. This basically tells to run R and avoid saving or restoring any workspaces that you have in your section. So typically when you run R script, maybe you've got a workspace in your current working directory or try and load it by default. Just doing -- vanilla. So don't tell me about complex stuff. Give me a vanilla session, just run whatever was in this current R script. An alternative is actually R command batch. And this is, I think, slightly more appealing because it also attaches the processing time to your results, your log files. But here you do R command batch, and you give it your R script, and it will run and evaluate. So these are just ways that once you put all the things you want to do in an R script, you can evaluate them non-interactively. If you're going to evaluate something non-interactively, you may want to supply some arguments, right? So I might want to say, have a script which works on a particular file, but I might want to change that file. I might have an R script which reads the file, normalizes the data, saves a new file. Okay, but the one thing I want to change is the name of the file. So you can add to the top of your R script this args, command args equals true. Okay, and in this case, when I run my R script, I can actually provide additional arguments after this part here. So I just provide additional arguments here. They get passed to the R function, and they're actually captured here in this vector args. Okay, so I might want to pass in my name of a file, whatever. One thing too, which will catch a lot of people is that, and I think this is the same for most languages, you can never pass in an argument which is a number. It always tries to treat it as a string. So if I want to say pass in a number which I want to multiply a particular column by or something, when I pass it in, it will be a string, and we just need to use one of these clever converting kind of functions like as.numeric to turn that into a numeric before we start dealing with it. Okay? I just know that a lot of people, when they start writing scripts, this is something daft which captures them, confuses them. Because, why is my number not being treated like numbers? Because any argument you ever pass it on the command line is treated as a string. So I think that's at the end of our session for intro to R. I know it's very quick. I'm here now to answer any questions. I think we had some good ones. I'm going to say, so I showed you in the first session. If you don't know, I'll show you again now. Just ask me. If you need to raise, if you have any questions, the first thing to do is ask me here now, and ask you along in the back. Never going to have, he does this every day, I do this every day. Sure, between us, we can answer your questions. Even if you ask me a question, I answer it if I feel like a question. But if I feel like it's common enough, I might raise an issue, I invite you to raise an issue in our GitHub. And there, everyone who ever comes to this class can see your questions. That's a good and a bad thing, depending on the question. But trust me, there are no stupid questions. It's not a challenge. If you ask them there, you really are helping them. So I invite you to ask questions. Google, local friendly bioinformaticians, ask us. Stack Overflow, and the most unfriendly place in the entire world are help. I wish I pulled up an example, but Stack Overflow, and R help, there are rules to posting. Read the rules first. Otherwise, they'll tell you to go read the rules first. And they will chastise you publicly in their forum. Our help, there's famously, do you know Brian Ripley? Brian Ripley. Am I being recorded still? But you know, famously people ask, dear Dr. Ripley, I have this problem in R. And he goes, oh, I'll ask my wife, Dr. Ripley, because he's Professor Ripley, and he's not going to answer your question until you address the message. So I recommend asking here, but you know, if you have any problems on things like Stack Overflow or our help, we can also help you construct the question. And what they're going to ask for you is a reproducible example. There are ways in R now, they have this package called Reprex, which allows you to build reproducible examples. So POSIT kind of force you to use this. We're not going to cover this in class unless someone has a bad experience on the R help. I'm happy to show. Maybe Alan, maybe we could put together an example. I did put one in R help, and I was naive, and I got some serious crap from this guy. So that's the end of the session for today. I'm going to stop my recording and cut